nodes given my strategy and belief. So the whole thing on the left-hand side is my subjective probability distribution over observable outcomes of the game. On the right-hand side, we have the same thing, except that instead of the conjecture about my opponents, I have the actual strategy of my opponents and the actual probability of moves by nature. So on the right-hand side, we have the objective probability distribution over observable outcomes of the game. Okay, the hard part is over. Once I define observational consistency this way, defining equilibrium is relatively straightforward. Equilibrium is a profile of strategies, beliefs, and posterior functions such that each player's strategy is subjectively sequentially rational, meaning they're doing the best they can at every point of the game, at every information set of the game, given their belief. Each belief is observation consistent. And here's a new part. It maximizes the entropy. The belief maximizes the entropy over the terminal nodes of the game among the ones that are observation consistent. And lastly, each posterior function, the probability distribution over nodes when you arrive at each information set, that satisfies Bayes' rule using your strategy and your conjecture about what others are doing. So that is the definition of equilibrium. Given this setup, I have three main results. First, does this solution exist? The answer is yes. Every finite extensive form game with perfect recall and observation constraint has an MOE. So any dynamic strategic situation, there is some prediction where people are best responding to possibly wrong beliefs, but those beliefs are sustained because they fit the data that they observe. Is this useful? My answer is also yes. MOE captures common causal misperceptions such as correlation neglect, omitted variable bias, also known as selection neglect, and simultaneity bias, also known as reverse causality bias. This solution concept is also useful because it's compatible with rational expectations. It's compatible with standard solution concepts, namely, if agents have perfect observation of outcomes, that is the map between outcomes to observable outcomes is identity. So all the terminal nodes are observable. Then my weaker concept, without requiring the maximum entropy, it coincides with self-confirming equilibrium. And the refined concept with the maximum entropy condition, MOE, coincides with perfect Bayesian equilibrium. Now, these results contribute to the literature by bridging behavioral game theory and standard game theory. I'm just showing you a big picture here. We have on the one hand, the behavioral theory of causal misperception led by Ronnie Spiegler and his co-authors. They focus on single person decisions. They use directed acyclic graphs to represent causal misperception by each player. The causal misperception is either exogenous or made endogenous by letting players have motivated beliefs. Motivated beliefs meaning they choose their misperception to maximize their subjective expected payoff. So given these setup, agents are subjectively best responding. On the other hand, we have standard game theory. We have multiple players with rational expectations assumptions. They know the strategies of their opponents, and objectively best respond to them. I think of my paper as bridging between those two, where I have a standard finite extensible game, add the linear map, the observational structure that allows multiple players, and the causal misperception arise endogenously from observational structure. And to have a sharper prediction, I add a refinement using maximum entropy criterion. So in this setting, players subjectively best respond to their beliefs.
Excuse me. But does anything to anything about directed acyclic graphs come into it, or is that
In my framework, I don't refer to directed acyclic graph at all.
okay?
Um,
But it's connected somehow through the fact that you're modeling causality or
yeah, it
perception.
is connected through maximum entropy. Ronnie Spiegler has a paper where he justifies using directed acyclic graphs from the principle of maximum entropy. So in that sense, it is connected.
Okay,
But
thank you.
you're correct. Yes, I don't directly use this DAG framework. So I've given you the overview of everything. Um, I want to spend some significant time on giving you the simplest example. This is a one-player game. Um, here, uh, there's a player who chooses to either smoke s equals 1 or not, s equals 0. If he smokes, he gets cancer with probability 2/3. If not, he gets cancer with probability 1/3. So in this setting, smoking causes cancer in the sense that it increases the probability of cancer. The player gets a small reward R, let's say smaller than 1/3 if he smokes, and loses 1 if he gets cancer. Here, the player's strategy is the probability sigma between 0 and 1 of smoking. So I have a illustration here of the decision tree. There's a player, he smokes with probability sigma. Nature can give him cancer with probability 2/3, in which case the player gets a small reward R, but no health benefit. If he smokes and get no cancer, he gets both the reward and health benefit. If he doesn't smoke and get cancer, he gets nothing. If he doesn't smoke and no cancer, he has no reward, but he does get health benefit. So in this setup, a player's belief is a pair of numbers, beta naught and beta 1, where beta s is the subjective probability of getting cancer given the smoking decision s. So it is a conjecture about this probability and conjecture about this probability. So you can see immediately that if we assume rational expectations, meaning the player has a correct belief, then he shouldn't smoke because the causal effect of smoking on cancer, which is the expected reduction in my health benefit, is larger than the reward R. So if you use any standard concept, perfect Bayesian equilibrium, Nash equilibrium, the prediction is don't smoke. Uh, Now I want to introduce causal misperception. So I will introduce observational consistency. Here, my framework includes the model includes a game and observational structure. So let's assume some observational structure. Let's say that player observes only the marginal probability of cancer. So the interpretation is that there's a population of players, and among that population, he only sees the marginal frequency of cancer. Given strategy sigma, a belief is observation consistent if it satisfies this equation, where on the left-hand side, we have the probability of smoking and probability of getting cancer, given that I smoke. probability of not smoking, and probability of getting cancer given that I don't smoke. So on the left-hand side, we have perceived marginal probability of cancer. On the right-hand side, we have the same thing, except we have the actual probabilities of moves by nature. So on the right-hand side, we have the actual marginal probability of cancer. So a belief is observation consistent if it generates the same perceived marginal probability of cancer as the actual marginal probability. The interpretation here is that a player sees a population of players just like himself, choosing sigma and seeing the overall rate of cancer patients, but don't know the conditional probabilities. But we'll see immediately that there are many observation consistent beliefs. I have a picture for you. Here's an illustration of observational consistency. For now, let's suppose that the smoking rate is 0.5. Half of the population smoke. Here is what nature really does. The player smokes with 0.5 probability, and nature gives him cancer with 2/3 probability. So people end up in this terminal node with 33% probability. Smoker doesn't smoke, then get cancer. People end up here with 17% of probability. But only the sum of these probabilities are observable, so the 50% in the population. That is observationally consistent with this belief, where the player believes that he gets cancer with 60% probability if he smokes and 40% probability if he doesn't smoke. It generates the same sum of probabilities, 30 plus 20, so total 50% of marginal cancer rate. So in this sense, this belief is consistent with observation. But this is not the only belief that is observationally consistent. We could have put 0.5 over here at the cancer probability given smoking, and also 0.5 here on the cancer probability given not smoking. That would have generated 25% probability here, 25 here. The sum is still 50. We could have put 1 here, 100% here, 0% here. That would have led to 50% on this terminal node, 0 over here. Still, the sum is 50%. So we have a spectrum of observation consistent belief that fit the same data.
Yes.
Which,
Sorry, I was just going to
oh,
say
go
the
ahead.
example numbers you have on what you think nature does are kind of ordinally correct, right?
Ordinally correct means,
Well, you
what
you
does it mean? Mhm.
think that smoking increases your chance of cancer still, but you get the numbers wrong. So that's,
Yes,
yeah, I suppose that could still
yes.
affect things. But I'm just thinking of from a plausibility point of view, right? You might have some idea
Uh,
or some restriction of what you know might be less than the truth, but still okay. Anyway, go on, please.
yeah, that's right. Here in this particular example, he at least qualitatively correct. Yes, he still thinks smoking increases cancer. The causal effect is positive, but not as big as as the truth. So this multiplicity of observation consistent belief lead me to appeal to the principle of maximum entropy. Here is some notation. Bold P, given my strategy and conjecture, is a vector of probabilities over the 4 terminal nodes generated by the strategy and belief. And G is the Shannon entropy function. In a standard way, if you have a probability vector bold Q, then it's the sum across the each component probability with this formula. So given a strategy, for now, let's say strictly between 0 and 1, an observation consistent belief maximizes the entropy. If it satisfies this, it maximizes the Shannon entropy of the subjective probability over the terminal nodes given my strategy and belief among the ones that are observation consistent. The interpretation here is that among many worldviews consistent with observation, the agent believes in the one that assumes the least amount of information. So entropy is the measure of randomness in the data. So maximizing entropy is minimizing the amount of information, hence this interpretation. It turns out that in this case, in this case, we have this illustration of maximum entropy, which produces a point prediction on belief. Here's a picture. The four corners of this simplex are the four terminal nodes of this decision problem. So any point in this simplex represent the probability distribution over the terminal nodes. And because I have my own strategy, it already pins down the possible distribution over the terminal nodes to this plane. And if we know the objective probability, then we would have just a point. For example, over here, but the player doesn't know the objective probabilities. He only knows the marginal probabilities. So that's going to give him some set of points that are observationally consistent. For example, this line segment here. So among these observation consistent belief, the maximum entropy criterion chooses a point, for example, here, that is conceptually closest to the center of this simplex. It is the belief that is closest to the uniform distribution among the observation consistent ones. So it turns out that in this toy example, maximum entropy implies correlation neglect. Here's a claim. For every strategy sigma strictly between 0 and 1, the maximum entropy belief satisfies this. The player thinks that the probability of getting cancer given not smoking and smoking is the same, and it's a marginal probability of getting cancer in the population. The meaning here is that player doesn't think smoking causes cancer. The intuition here is that player observe no evidence of dependence between smoking and cancer. So the belief that assumes the least amount of information given this evidence is to believe in no correlation. There's a more general result in mathematical statistics and statistical physics that correlation neglect is actually a defining feature of maximum entropy. Whenever agents observe only the marginal probability distribution between two variables. In our case, that was the player knowing his own strategy. So he knows the marginal probability of smoking, and he also knows the marginal probability of cancer. So given those two marginals, but not joint probabilities, the maximum entropy belief fitting that observation is the one that assumes no correlation. Okay, so far we've assumed a strategy and looked at what is the maximum entropy belief. Now let's talk about equilibrium, defined just for smoker's problem, so that given that belief, the strategy is a best response to that belief. Here's a definition. A strategy belief pair is an observation consistent equilibrium OE if given the belief, the strategy is a best response, and given the strategy, the belief is observation consistent. The interpretation here is that OE is a prediction of how the player behaves, given his possibly wrong but observationally consistent belief. It turns out that OE may be too permissive, predictably so, because typically there's a spectrum of beliefs that are observationally consistent. Namely, in this setting, every strategy is rationalizable by some observation consistent belief. Here's a claim. Every strategy sigma has a belief such that the strategy belief pair is an OE. Specifically, the OEs look like this. So for the strategy of never smoking, there is some belief that is observationally consistent. He thinks that the harm from smoking is greater than the reward. So the best response to that is never smoke. There's also some belief that justifies always smoking. So also observationally consistent. And he thinks that the harm from smoking is smaller than the reward. And if he's mixing, there is some belief that makes smoking and not smoking indifferent. So the idea behind this large set of OEs is that because there are many observation consistent beliefs, there are many OEs. Which leads me to define the refinement, the maximum entropy OE. Here is the definition of MOE. An OE is a maximum entropy observation consistent equilibrium MOE if on top of satisfying the requirements of an OE, if the belief beta maximizes the entropy given the strategy sigma. So that is the case if the strategy is strictly between 0 and 1. If it's on the boundary, I need to define it as some limit of interior strategy and interior maximum entropy belief to avoid multiplicity of solution to this maximum entropy. The interpretation is that MOE is an OE with an extra requirement that the player believes in the simplest explanation consistent with observation. Now, with this refinement, MOE gives a unique solution. It provides a sharper prediction. Here's a claim. A strategy belief pair is an MOE if and only if sigma equals 1, thus the player smokes all the time, thinking that the probabilities of getting cancer is 2/3 regardless of smoking or not. The meaning here is that the player keeps smoking while thinking that smoking doesn't cause cancer. And the intuition is that maximum entropy belief features correlation neglect. So no other strategy can be a best response.
Hang on. Could you just go back to
Yeah,
your
Johnny.
definition on the previous slide?
Mhm.
Previous slide, please.
Mhm.
Okay. If it, no,
Oh,
next one. Yeah.
mhm.
Okay. It's maximum entropy equilibrium. If it does that, okay, then you've got the definition below for the limit. Okay, got it.
Yeah, that's right. That's
I
right.
hadn't caught that just below there. I thought you'd restricted to interior sigmas, but I
That's
see.
right. Yeah, thanks for pointing out. Yeah, I need these definition with trembles so that um, the entropy is flat at the boundary. So I define it this way to have to be consistent with the interior solutions. Oh, Yannick, do you have a question?
Yeah, I was just surprised. I was expecting that the MOE would be that you believe there is no correlation, but then something like you could play 1/2 or something like that, right? So I mean, can you give us some intuition why you get this and not
Yeah.
something else?
Um,
I thought that, if you're saying that the probability of smoking is like 1/2. I thought that would maximize the entropy, so I was expecting something like that. But
right.
the
Yeah,
probability of having cancer would be 50%. That seemed as maximal entropy as I imagined. But so why do you get this?
yes. Yeah, thanks for pointing it out. So the important part is that the maximum entropy is only about the belief, but not the strategy. So given the maximum entropy belief, you gotta still be best responding. And the setup was that um, the there there is a reward from smoking, and there is a uh, potential harm from
Hmm.
getting cancer. And because the maximum entropy says, okay, there's no effect on the probability of cancer, I'm gonna best respond to that, which is just smoke and get the reward.
Yeah. Okay. Thank you.
Yeah, thank you. Um, so this is the simplest example. I have the first general result on the paper is existence. So every finite extensive form game with perfect recall and observational constraint has an MOE, meaning being there always exists a prediction where everyone sustains a maximum entropy belief, which is possibly wrong, generically wrong, about how others play and best responds to it. The proof uses Kakutani's fixed point theorem. So the key proof step is to show that the mappings satisfy the conditions of that fixed point result. So it goes with epsilon constraint strategies, then mappings from strategy profile to maximum entropy belief and posterior functions are all well behaved, meaning they're non-empty valued, convex valued, and upper hemi-continuous. So the key part is that maximum entropy, the belief, the solution to maximum entropy belief is well behaved enough to make the whole mapping well behaved. I want to give you one more example because I've only given you a toy one-player example. Here's a more fun one, a centipede game. Here's a 4-node centipede game, including 2 players. So it is like a standard centipede game where Alice could take and get $1, but potentially by passing, she could get a higher number of dollars. The claim here is that okay, the model consists of both the game and the observational structure. So here's the game. What is the observational structure? Let's suppose that players observes only the average number of passes. The interpretation is that, okay, we have these population of pairs of these players. And when you enter a game, you see how on average, how cooperative the games end up, but they don't know the exact outcomes. If that is the observational structure, then there exists no MOE in which Alice takes immediately. It depends on the value of these parameters, but unlike many standard solution concepts that cannot rule out taking immediately, the MOE rules out, in this case, taking immediately. Specifically, there is a unique MOE of this game where each thinks that the other mixes more than they actually do. So in this unique MOE, Alice passes all the time. Bob passes all the time. Alice mixes between these two, taking and mixing, taking and passing. And Bob, when he arrives here, he's always taking. So they're best responding to what they think others are doing. And in this equilibrium, this here is what Alice thinks Bob is doing. She thinks Bob is mixing someone. She attaches some probability of taking here, and she attaches some probability of Bob passing here. So she is hopeful that Bob once he reaches here, he's going to take. So this is the consequence of only observing the average outcome and the consequence of maximum entropy, which tends to attach probabilities that are closer to uniform than the player's actual strategies. Similarly, for Bob thinks Alice mixes more than she actually does. He thinks she mixes over here. She thinks Alice will pass, more likely to pass than she actually does. Okay, this is fun, but there is some limit to how much results I can derive given the general setup of just finite extensive form game. So now I'm gonna restrict some class of games and look at causal misperceptions that arise from more structure. But before I do that, I wanted to mention that the solution concept is nice because it's testable in the lab. So this new component observational structure is something that exists in the world and is manipulable. So here's an ideal experiment, which is to have lab subjects play a game with different observational structures, perfect and imperfect. we could randomly assign subjects to control and treated groups. And within each group, randomly match each subject with another and let them play one round of the game. Control players receive perfect feedback about all control outcomes. Treated players receive imperfect feedback about all treated outcomes, and repeat these steps sufficiently many rounds. An example is a simplified poker game, and I have a work in progress with experimental co-author. And we have just run the pilot data. So in poker, the standard poker game is when games end with a fold, you don't reveal your cards. So that is an imperfect observation structure that you don't precisely observe the terminal nodes. So we have that treatment against the control treatment where we reveal the cards always. We have some pilot data results. So if I have some time in the end, I will show you some of that results. Now I want to look at putting some more structure on the game and looking at what causal misperception arise from it. I have three cases in the paper, but I'm going to show you only the second case, omitted variable bias, also known as selection neglect. Here is what I call an omitted variable game. There are n players. There are 3 stages. Nature assigns a state with probability pi of t. Players see the state and chooses actions, x, a vector of actions, and nature chooses a consequence y with probability pi of y, conditional on both the state and the vector of actions. The important thing is that it depends on both the state and actions. The payoffs depend on state, actions, and outcomes. An example I think about is my labor market outcomes or my employment prospects depend on both my natural ability and my educational attainment. Let's say that the observational structure of this game is the marginal probability of the pair ability and actions and consequences, but not all 3 of them at the time. So a story about this would be that, okay, I attend school and I can observe how my classmates do based on their talent and how they do in school. And maybe I go on into the real world and I observe their CV, their resume, and how they do in the job, but I don't have the full I don't have the full data set of all 3. So given this game and observational structure, the MOE points to a belief that features omitted variable bias. Precisely, an OE is an MOE if and only if every player's belief satisfies this. So they have a belief about how nature plays. They have the correct belief about the probabilities over the states. They have correct beliefs about how others are playing given the states. So they have a correct belief about others' strategies, but they have incorrect belief about how the nature assigns the consequences, like labor market outcomes, conditional on state and action. Namely, it's some weighted average of actual conditional probabilities. Importantly, this thing on the right-hand side does not depend on the state T. So the meaning here is that players believe that the effect of X, their educational attainment on labor market outcomes, is the same across states. So this is like the classic omitted variable bias that people think that their chances of getting a good job only depends on their education, but not their abilities. So the ability is kind of the omitted variable here. Example is high school graduates may overestimate or underestimate the value of college education because they're missing that variable. Now I want to compare this solution concept with related concept because this kind of question comes up a lot. I want to first compare MOE, OE and MOE to standard concepts. Here's the proposition. Under perfect observation of outcomes, meaning that the observational structure is an identity, OE coincides with self-confirming equilibrium, a version with that requires sequential rationality. And the refinement MOE coincides with perfect Bayesian equilibrium. This has nice implication that if you have a model, if you have a standard model, and if you want to introduce causal misperception onto the existing model, the way to go is take the same model and vary the observational structure C. So the varying the extent of misperception on an existing model is pretty straightforward. I have comparisons with other concepts, such as analogy-based expectation equilibrium. They have similar motivation, but in that concept, players believe that others behave the same in analogous situations, where analogous situations are sets of different information sets. So this setup forces the modeler to define what are the analogous situations among the information sets of the game. In comparison, this part is given by observational structure over terminal nodes rather than information sets in MOE. People ask about the difference between MOE and cursed equilibrium and its recent extensions, cursed sequential equilibrium or sequential cursed equilibrium. In their setting, players believe others behave the same regardless of their types or information. They have an exogenous parameter that represents the cursedness. Instead of that, compared to that, MOE has a observational structure that is not just model parameter, but is manipulable. People also ask about what's the difference between MOE and Burke-Nash equilibrium. Burke-Nash equilibrium is quite different in that players' beliefs about the game itself are wrong. They are misspecified. So players have wrong idea about the game tree itself. In comparison, MOE assumes that players have the correct belief about the game tree. They just have incorrect beliefs about the strategies of other players. So here, yeah, I think I've given you a pretty good introduction to MOE. Here's a one sentence takeaway for you. MOE allows causal misperception in a dynamic model. It lets misperception arise endogenously from the observational structure, which is something concrete. It exists in the world, and it's manipulable in the lab. And MOE gives a point prediction on beliefs. Yeah, I'm going to pause and see if there are any questions.
Any intermediate questions? How does it relate to rational inattention?
Rational inattention, there's no direct connection. Rational
Make one.
inattention, excuse me?
Could you make one in theory? Could you add
Yeah.
some cost that would give you this?
Yeah, let me think about this. Yes, rational inattention assumes that there is some cost of collecting information. If I assume that the cost of collecting information is infinite and the cost of collecting information about what is observable is zero, then it seems that it will be equivalent to MOE. So there are things, Yeah, it is an extreme version of rational inattention where there are things that are observable. The cost of observing that is zero in MOE, and the cost of observing unobservable things is infinite. Um, it yes, it seems that is the connection.
Okay, I see. So it's you're turning things off and on rather than partially off and on, right? It's a
Yeah.
cost. Okay, thanks.
Um, okay, good. Since I've given you an intro to MOE, I want to show you some preliminary pilot results from the experiment, which I want to cover because it's a direct follow-up to this previous paper. It tests MOE in the lab. And this is with my co-author Irfan Khan, who is a rising sixth year graduate student at The Ohio State University. He's an experimenter. Here's what we do. Our question is, how does partial feedback or partial observational structure, imperfect observational structure, as in MOE, affect people's learning in games? Our design to answer this question is to have lab subjects play simplified poker. Our tentative answer from our pilot data is that only giving partial feedback, not giving their full observation, only giving them imperfect observation of terminal nodes, increases the frequency of a non-rationalizable play, increases the frequency of mistakes by 8 percentage points. So blocking them from observing the precise terminal nodes in this simplified poker setting made their mistakes more likely. Although this is a small sample pilot data. So let me give you more details. The motivation behind this work, other than testing the MOE, is that many games provide only partial feedback. In many games, players see results without observing the full history, full terminal node, full history of states, information, or actions, even after the game's end. For example, poker, when games end with a fold, you don't reveal the cards. Sealed bid auctions, we may know the winning bid, but we don't know how everyone else bid. Secret ballot voting, school choice mechanism, many of these examples, we have limited information about the precise terminal node even after the game's end. Despite this, please correct me if I'm wrong. Standard theories of learning assume that agents observe the precise terminal node after each round, which leads me to lead to our question: how does partial feedback shape learning and misperception about opponent strategies? Here's the experimental design. We use a classic game designed by Harold Kuhn all the way back from 1950. It's surprising that there is no experiment yet about this game. The game is moderately complex, maybe that's why. In each round, there are randomly matched players with fixed roles, player one or player two. They draw a card from a 3-card deck consisting only of king, queen, and jack. They draw cards without replacement and bet sequentially. And we let the subjects play for 31 rounds. We have 4 treatments. They are all incentivized, including belief elicitation at every 5 rounds. We have a baseline, the control group, where players have partial feedbacks. Players' cards remain hidden when games end with a fold. And we have reveal treatment or full feedback. Players' cards are revealed after all the games. We have 2 more treatments that mirror these earlier 2 treatments, alternating and alternating reveal. And players' roles are switched after every 5 rounds of games. Our hypotheses are that revealing cards after the game, so have full observational structure, and alternating roles, letting players switch roles after 5 rounds to be in their opponent's shoes, we hypothesize that these two things will improve both players' strategies, how they best respond to their beliefs, and the accuracy of the beliefs themselves. Here's more detail about Kun Poker. When the game starts, each player adds $5 to the pot, and both players draw cards from the 3-card deck. And the first player decides either to bet or check. Bet means you put $5 more into the pot. Then player 2 decides whether to fold or call. If he folds, then player 1 wins, and player 1 gets the pot. If player 2 calls, then we reveal the cards, and whoever has a higher card wins. If player 1 decides to check, then player 2 can either check or bet. If player 2 also checks, then we reveal the cards, and whoever has the higher card wins. Or player 2 could bet, in which case the turn goes back to player 1, who can either fold or call. So immediately, even without thinking about equilibrium, there are obvious predictions, which are: don't fold when you have a king, you have the highest card. Don't give up the game. And don't call with a jack when your opponent bets on you, because you know that you have the lowest card. So those are obvious predictions. These are like the immediately strictly dominated moves at the first round. But once we eliminate these obviously stupid moves, there are strictly dominated moves at the second round, which is less obvious prediction, which is to not bet with a queen. So compared to betting with a queen, checking is better, because you know when you have a queen that your opponent is going to have either jack, in which case your opponent's going to fold anyway, so there's no benefit, or your opponent is going to have a king, in which case he will beat you, so you just wasted money by betting. So the strictly dominant strategy is to check when you have a queen. Okay, let's see some results. And before giving you the results, here are some long-run predictions from literature. First, the standard concepts of Nash and self-confirming equilibrium, they're the same in this game. In the standard concepts, different feedback structures don't predict different strategies. Kurz's sequential equilibrium do not have a concept of feedback structure or observational structure, but the different feedback structures are interpreted as different Kurz's parameters that predict different strategies and beliefs. In comparison, observation-consistent equilibrium, OE, different feedback structures directly predict different strategies and beliefs, and in particular, MOE, the one that requires maximum entropy belief, predicts that players believe their opponents play more randomly, closer to uniform than they really do. Here are our pilot results. We're looking at the last 10 rounds out of total 31 rounds that seem to more or less converge to some distribution over strategies. First, here are player one's data on average across subjects across the last 10 rounds. On the leftmost column, we have move frequencies. So this is player one's bet rate, how frequently they bet given their cards jack, queen, or king. And over here we have player one's call rate – after player one checks and player two bets. conditional on the player one having jack, queen, or king. We said that we predict that you should not call when you have a jack, and you should excuse me. You should always call when you have a king, and you should not call when you have a jack. And subjects are doing these kind of first round strictly dominant strategies pretty well. Most of them avoid making the mistake of calling when they have a jack, and they avoid folding when they have a king. So they're doing this first round strictly dominant strategies pretty well. What they don't do well is avoiding a second round strictly dominant strategy of betting when they have a queen. When they have a queen as a first player, 37% of them in the baseline treatment of revealing the cards with fixed rows, 37% of them do bet when they're supposed to not avoid betting and rather checking. So 37% of players are making mistakes in this situation. Revealing the cards seem to help them a bit by lowering this frequency of stupid moves by about 8 percentage points. And alternating the rows also helps quite a bit. We have a bit confusing result here. When we alternate and reveal, it's not as helpful as doing one at a time. But overall, it's still helpful compared to the baseline. We also elicit beliefs about the players. Beliefs are pretty noisy, but what is notable from the beliefs about player one, so this is about asking all the subjects, what do you think your opponent, who is a player one, will do when they are in this situation, when they have a jack and they're deciding between bet and check or call and fold. So interestingly, subjects think that their opponents make about 20% of the time mistakes. So they think their opponents are going to call 20% of the time, even with jack. So these numbers point to the beliefs minus the actual strategy. So actual strategies were 0. So subjects think their opponents make mistakes 20% of the time. It's similar for their beliefs about the mistakes of their opponents when player one has a king. They think their opponents who have a king will fold 20% of the time. So they think their opponents are more stupid than they themselves. Now let's go to the strategies of player twos. We have some confusing results where the beliefs seem to be opposite. Subjects are still doing well as player two. They avoid calling when they have a jack. They avoid folding when they have a king. They still do those well. When they have a queen, they bet 25% of the time. They make mistakes 25% of the time. And revealing the cards doesn't seem to help. It increases the queen bet rate. Same with alternating. And both alternating and revealing seem to confuse them a lot. Similar pattern with beliefs about player two's moves. Here we also see that players think that their opponents make more mistakes than they themselves. Okay, that's all the data I wanted to show you from our pilot experiments. At first glance, based on the pilot data, it seems that subjects play non-rationalizable strategies pretty often. Revealing the cards help reduce those moves in some cases. Based on our belief elicitation, players have beliefs that are significantly off toward 50-50 about their opponents, even though their opponents are playing the obviously strategic, obviously dominant moves correctly. And those beliefs from this small sample pilot data don't vary that much different across treatments. So our conclusion from our pilot results is that, okay, we need a greater sample size. So we're going to run the main experiment. We are going to go with this setup and find out more precisely. Thank you.
Okay, thank you very much, Sungmin.